Hi there. In this video, I will be working through the handout on some of these preliminaries for trigonometry. So we need to go over some things that you've probably seen before that we will be using pretty frequently to better understand trig. So here's a big idea, right? Before we just call it a theorem, let's think about what's so important about this. If we know any two sides of a right triangle, if I have a triangle with a 90-degree angle, I have these three sides, A, B, and C. It turns out if I know any two of them, A and B, or A and C, or B and C, I can definitely figure out what the third one is. And how we do that is the Pythagorean theorem. So it's called the Pythagorean theorem, named after a person named Pythagoras. And what it says is, in a right triangle, where C is the longest side, called the hypotenuse, and the other sides are called A and B, A squared plus B squared equals C squared. This is true in a right triangle. This is not true in other kinds of triangles. So in a right triangle, A squared plus B squared equals C squared, where C is the hypotenuse, and A and B, oh, let's not put plus, that looks like math. A and B are legs. Right? And maybe you don't remember this vocabulary. You probably saw it in geometry. The longest side in a right triangle, you can see it up here, the one that's across from the right angle, is called the hypotenuse. That word is only used when we're talking about a right triangle. And the other two sides are called legs. So a right triangle has one hypotenuse and two legs. And this equation right here tells us how those three numbers are related. So if we know two of them, we can solve for the other. So as an example, right, so here are some examples. I should have formatted that a little bit better. So let's suppose we have a right triangle like so, where this is 5 and this is 12 and this is x. Let's not get caught up on the names A, B, and C. Let's just say legs and a hypotenuse. Here the hypotenuse is called x. Our rule here is leg squared plus leg squared equals hypotenuse squared. 5 squared is 25, 12 squared is 144. Add those together, we get 169. And if you take the square root of this, it actually works out to a nice whole number 13. That one is a famous example where all of them are whole numbers. That doesn't happen all the time. So here, for example, let's suppose I have that this is 4 and this is 10, and we want to find this. And I'm going to call it C, even though it's not the hypotenuse, so that you pay attention to the pattern and not just memorizing A squared plus B squared equals C squared. So leg squared plus leg squared equals hypotenuse squared. We have 16 plus C squared equals 100. So C squared equals 84 if we subtract. C equals the square root of 84. And that simplifies, but we'll talk about how to simplify radicals in a little bit. So whatever the square root of 84 is, maybe you put it in your calculator, maybe you simplify by hand. Some version of that is our correct answer. Okay, now moving on, another big idea. When we have a special right triangle, so special right triangle usually refers to a right triangle where the angles have very nice measures in terms of their degrees. One example of a special right triangle is what's called a 45-45-90 triangle. So it has two angles that are 45 degrees and one that's 90 degrees. 45 plus 45 equals 90. 45 is half of 90. So there's a really nice relationship there. The other really nice one is 30, 60, 90. Right? 3 times 30 is equal to 90. So 30 and 90 really play well together. The other one is 60. If we have one of these special right triangles, we only need to know one of the sides. And there's enough information to find the other ones. Again, something you probably saw in geometry. So here's the rule for a 30, 60, 90 triangle. And I'm going to give you one version of it. There are other ways of expressing this. So I'm going to just draw this by hand. I will do my best to draw something where I really feel like this angle here looks like it's about 30 degrees. This angle here looks like it's about 60 degrees. One of those angles is definitely bigger. And of the two legs, one of them is definitely longer than the other. So here, this is our short leg. And let's just generically call that, say, A. If the short leg is A in a 30, 60, 90 triangle, the hypotenuse is exactly twice as long. It's 2 times A. The long leg will be A times the square root of 3. So square root of 3 is an irrational number. Sometimes we would put this computation into our calculator to get a better understanding. But for now, let's just say square root of 3 is a certain number. Right? It's approximately 1.7. We'll talk about that more later on. When we multiply by that number, we get the longer leg. So quick example. I will try my best to draw something that looks like a 30, 60, 90 triangle, but I'll make the orientation look a little bit different. If I told you that this was 4, then we would know that the hypotenuse here is 8, exactly 2 times 4. And the longer leg would be 4 times the square root of 3. If you put that in your calculator, I will do that right now. 4 times the square root of 3 is approximately 6.928. So very close to 7. And hopefully that looks believable in the picture. I didn't pull out a ruler to do this, but to me, those numbers look about right. Or maybe I have a 30, 60, 90 triangle like so. Change the orientation again so you get used to seeing them different ways. Maybe I told you that this is 6. Let's just label these as X and Y. So what we know is that the longer leg is the shorter leg times the square root of 3. So I could just write 6, the longer leg, equals the shorter leg times the square root of 3. So x would be 6 divided by the square root of 3. We'll talk about how to simplify that later. Let's just take this as a version of the answer. And we know that y is twice as long as x. So that would be 2 times 6 over root 3. If you're not 100% sure how to multiply that out intuitively, remember that 2 is the same as the fraction 2 over 1. So you can use your old factoring rules, and this would be 12 over root 3, which again simplifies, but we'll talk about that later. So these are some examples. You'll have a lot more to practice. But what you want to know is if you have a 30, 60, 90 triangle, there are rules, and you need to know these. These are going to come up over and over and over and over again. So you want to make sure you really know them well. Don't just say, oh, I do something with the square root of 3. That's not specific enough. You need to understand specifically how each side is related to the others. If we have a 45, 45, 90 triangle, we might notice this has 2 angles of the same size. That means it will also have 2 sides of the same size. So if I call this b, this is also b, and this is b times the square root of 2. You can actually figure that out by doing the Pythagorean theorem. Square root of 2 is approximately 1.4. So as an example, if I have a 45, 45, 90 triangle like so, I should label these over here. Here's 45 degrees, here's 45 degrees. Did I label these others? I really should label at least one of these so that we know it is 30, 60, 90 and we're not guessing. This one here is 45, 45, 90. So here, suppose I told you this side was 5. Well, that would mean this one's also 5, and this one is 5 times the square root of 2. If you put that in your calculator, you're going to get something around 7. Let me do it right now. 5 times the square root of 2 is approximately 7.071. If we had an example where we already knew the hypotenuse, So here's our 45, 45, 90. Right, you might remember all the angles add up to 180. So if I mark two of them, the other one has to be the other one, we know by just subtracting. If I told you, say this was 8, and this is A, this is the same thing. I know that A times the square root of 2 equals the hypotenuse. So A is 8 divided by the square root of 2, which we can simplify later on. But this is a version of the answer. So know these, right? Know these. Not just basic familiarity. You should be able to explain these in detail. You saw these last year in geometry. Maybe you've forgotten them. But really take the time to 100% know these relationships cold. It'll make the rest of trig so much easier for you. All right, let me just mention some important things. So I have some bullet points here. When you draw one of these special right triangles, really make an effort to do so accurately. I'm not saying you need to pull out a ruler or a protractor, but when you're drawing a 45, 45, 90, you should remember that in a 45, 45, 90 triangle, the legs are the same length. So, ask yourself, am I drawing it where this distance here and this distance here look roughly the same? It doesn't have to be perfect, but you want it to be believable if you wind up marking that these are the same length. In a 30, 60, 90 triangle, the 60-degree angle is definitely bigger than the 30-degree angle, and one of the legs is definitely bigger than the other one. You should be drawing a triangle where, without any hesitation, if you look at the two different legs, you know which one is bigger. And if you look at these two angles that are not right angles, you know which one is bigger. Don't put yourself in a situation where you're trying to figure it out. You want it to be really obvious. Yeah, here's the 60-degree angle. Here's the 30-degree angle. Here's my shorter leg. Here's my longer leg. And obviously this one, we don't use the word leg. There's my hypotenuse. Now, when we work with special right triangles and we start using these rules in trigonometry, certain irrational numbers, certain numbers expressed using radicals that don't come out particularly nice, and we have to approximate them on our calculator, certain numbers are going to come up over and over again. And it's really nice if you know roughly how big these are, right? The number square root of 2 feels very mysterious, but if you put it in your calculator, it has a value. Same with the square root of 3. Sometimes we'll be taking those numbers and dividing them by 2. So square root of 2 divided by 2, which is the same as 1/2 square root of 2. Or perhaps square root of 3 divided by 2, same as 1/2 square root of 3. You're going to see these numbers a lot. So it's nice if you know roughly how big these are. So the square root of 2 is roughly 1.414. If you remember this as 1.4, that's good enough. Right? And just to make sense of this, if you get stuck, even if you don't have your calculator, right, 1.4 times 1.4, if you multiply that out, right, that's going to come out to 1.96. Here, I'll actually do it. Right? 4 times 14 is 56. 1 times 14 is 14. It's 196 with 2 decimal places. That's just a little bit less than 2. So a number really close to 1.4, if we square it, we get 2. So we're going to have a lot of examples where we multiply a length by this number, square root of 2. If you multiply a length by the square root of 2, you're going to get something that's roughly 40% longer. You're multiplying by 1.4. You're multiplying by 140%. That makes it 40% longer. Right, let's look at an example right here. I'm going to hop around a little bit. Here's an example of a 45, 45, 90 triangle. If this is x, this is x times the square root of 2. And hopefully this feels believable. I'm not going to pull out a ruler. But if I look at these two sides, the one in red is definitely longer than the one in green. But it's not much, much longer. It should be believable that, yeah, it's like 1.5 times as long. Right? It's more like 1.4 times as long. It's about 40% longer. If that looks like 50% longer, you're in the right ballpark. right? These numbers should have a meaning. I'm taking something and I'm multiplying it by the square root of 2. That means it's like I'm multiplying it by 1.4. The thing in red should look like I took the thing in green and made it about 40% longer. Square root of 3 is approximately 1.732. If you remember that as 1.7, that's definitely good enough. So if we multiply by a length by square root of 3, we're going to get something that's about 170% as long. So 70% longer. Right? It's much longer, but it's not twice as long. Right? It's not 100% longer. It's 70% longer. Let's look at another example. So here we have a 30, 60, 90 triangle. And I tried to get a perfect one. Online, I found a picture where the angles hopefully are perfect. Perfectly 30 degrees, perfectly 60 degrees. If this is A, then this longer leg is A times the square root of 3. If we were to look at these, hopefully it is believable that this leg here is almost twice as long. Right? If I really tried to measure out how long this red thing is, I'm going to try it. I'm going to try to copy that red thing at exactly the same length. Right? So I feel like here's one of those, and then another one would be like that. We're looking at something that is almost twice as long. Right? It's not exactly twice as long. Right? It's about 170%. It's about 70% longer. These numbers should have some meaning so that you're not just memorizing a bunch of things you don't understand. Yeah, when I go from the short leg to a long leg in a 30, 60, 90 triangle, it is predictably about 70% longer. Sometimes we see these irrational numbers with fractions. If we have square root of 2 divided by 2, that's about 0.7, about 70%. So if we multiply something by this number, it's about 70% as long. It's shorter, but it's more than half, right? It's somewhere between half as long and the full length. Again, let's look at an example. Here's a 45, 45, 90 triangle. If this is called y, I will tell you that this here is y times root 2 over 2. You don't have to worry about how I got that right now. I'm just going to tell you that this number comes up, and when we do the math and simplify the radicals, that's the computation. This is about 70%. Does this look right? I hope so. I'm taking this red thing, and then this purple thing. Does it look like the purple thing is about 70% as long as the red? Purple is approximately 70% as long as the red. That seems very believable in this picture. The exact number is not perfectly 70%. It's this number, square root of 2 over 2. But you should remember, okay, square root of 2 over 2, when I put that in my calculator, I get something that's around 70%. Sometimes square root of 3 over 2 comes up. If I multiply by that number, I get something that's about 87% as long, right? 0.866, it's 86%, 87%. Frankly, if you just want to remember this as like close to 90%, that's good enough. It's when we multiply by that number, we get something that's smaller, but not a lot smaller. We get something that's almost as big as the original. So as an example here, if here's my 30, 60, 90 triangle, if this is C, this long leg is C times square root of 3 over 2. Right? It's multiplying by that number that's in the ballpark of 90%. Here's the purple. Here's the green. The purple is longer, but the purple is not much longer. So the green is about 87% as long as the purple. That's the approximate value of this exotic number, square root of 3 over 2, but it should look believable. I know maybe you haven't reviewed radicals too much, but come back to this. As you do more examples where there are 30, 60, 90 triangles and you see these numbers, really pause to think about the meanings. So here are some exercises. Now I'm going to zip through these. If you did, hopefully you saw this in class. If you're catching up after the fact, pause for each one of these and really do it on your own. But I'm just going to zip through so that I can finish the video faster. So draw a 30, 60, 90 triangle where the shorter leg has a length of 7. So first of all, we just want to practice drawing these in a reasonable way. Right, 30, 60, 90, definitely one of the legs is longer than the other. So I'm saying this is 7. Right, so I'm just kind of thinking like ballpark. If this is 7, right, to me, this looks like, you know, it's something like 13, and this is something like 15. I'm just trying to use my number sense. I obviously drew this by hand. It's not perfect. Right, those are my guesses. Now, if I actually do the work, I know that the rule is that this is 7 times 2. So it's exactly 14, which hopefully looks believable. This is 7 times the square root of 3. And let's use our calculator here. Let's actually get a decimal on this. So 7 times the square root of 3, I'll just round it to one decimal place, is 12.1. I think I estimated 13. These aren't going to be perfect, but we want to be in the ballpark. We want to look at this and know that this length is not 3, it's not 45, it's something like 11 or 12 or 13 or 14. Because occasionally we make silly mistakes and we want them to be obvious. All right, what if we have 30, 60, 90 where hypotenuse is 10? Again, I'm drawing them by hand, so they're not perfect. But we want them to be close enough that the numbers seem believable. Right? To me, this looks like 5 or 6. To me, this looks like 9-ish, just rounding things to a whole number. Right? What's the actual rule? Well, we know the rule is that short leg times 2 equals the hypotenuse, so 5 is the correct one. And then what do we get over here? We know the long leg would be 5 times the square root of 3. If I put that in my calculator, 5 times the square root of 3, that is approximately 8.7, just rounded to one decimal place. So my estimate was pretty good. 45, 45, 90 triangle where the leg has a length of 3. Here's 45 degrees, so we're saying this is 3, this is 3. All right, this is something like 4 or 5. What's the actual value? The actual value is 3 times the square root of 2. If I put that in my calculator, just to one decimal place as a reality check, 4.2. Right, that's in our ballpark of what we think it should be. Okay, 45, 45, 90 triangle where the hypotenuse has a length of 12. Just while I'm here, I will mention there will be videos for most of the sections in this book and most of the handouts. If you want extra practice, if you didn't understand something in class, if you were absent, these are a resource. I definitely go faster in these videos. So if you're trying to make sense of this, right, pause a lot. Think about what I'm doing. Don't just assume that at the speed I'm doing this, I'm expecting you to understand everything. Maybe watch it multiple times, maybe do a lot of pausing. Nobody learns as fast as I'm talking right now. If I call this A, I know these are the same. Right? And I'm thinking to myself, okay, if this is 12, you know, this looks like it's something like 8 or 9, somewhere in that ballpark. It's more than half of 12, but it's definitely smaller than 12. The rule is that A times the square root of 2 equals 12. So A would be 12 divided by the square root of 2. I'll put that in my calculator. And that comes out to approximately 8.5. So my ballpark, just from the picture, yeah, it looks like 8 or 9. Yeah, it's about 8.5. As you're doing examples with triangles, it's really nice if you have a sense of what numbers make sense, so that if you do make an error, it's obvious. Okay. We're doing a lot with radicals. Ideally, when we have expressions with radicals and we're not putting them in our calculator, we want them simplified. And there are two things to keep in mind for simplifying radicals. So here's one strategy. Keep the number under the radical as small as possible. So we want to look at the number we're taking the square root of and asking, can I rewrite this to factor it using a perfect square? And let's just remember, perfect squares mean the numbers we get when we square things. 1 squared is 1, which isn't interesting, but 2 squared is 4, 3 squared is 9, 4 squared is 16. We want to be on the lookout for numbers that are divisible by these other numbers. I'll go up to 10. If one of these numbers is a factor of what you're looking at, it means there's an easier way to write your answer. So here I might notice 300 is 3 times 100. 100 is a perfect square. So I can say that the square root of 300, right, that's 3 times 100 under the radical. We are allowed to break this up. If we are multiplying, we can say the square root of 3 times 100 is the square root of 3 times the square root of 100. And the square root of 100 is simply the number 10. So here we have the square root of 3. 3 is a really small number. We can't simplify this, times the number 10. And typically we write this so that the non-radical part comes first and the radical part comes second. So the way people would usually present this in simplified form is 10 times the square root of 3. Square root of 72, you might notice 72 is 2 times 36. If you didn't notice it that way, you can just do it with more steps. So this is 36 times 2. So it's the square root of 36 times the square root of 2. Square root of 36, which is 6, times the square root of 2. This would be our most simplified answer. So this way of breaking up the radicals works when we're talking about factoring or multiplication or division. All right, let's just look at this example. We know these. The square root of 4 is 2. The square root of 9 is 3. The square root of 36 is 6. 2 times 3 equals 6. 4 times 9 equals 36. Right, so the idea is when we have multiplication, this equation, let me write this clearer. This equation, 4 times 9 equals 36, is true without the square roots. But if I put every number under a square root, it's still true. That is something we can do when we have multiplication or division. You just throw a square root on every number and it's still true. That is not a rule. We can't do it when there's addition and subtraction. Right? If we have the square root of 4 plus the square root of 9, that's not the same as the square root of 13. Because this is 2 plus 3. 2 plus 3 is 5. 5 is not the square root of 13. If I take 5 and square it, I'm definitely not going to get 13. So be really aware of this. Many students have trouble with this. You're allowed to simplify radicals, but the simplification always uses multiplication or division. Because square root is like squaring. Squaring is a kind of multiplication. So it makes sense that since squaring is a kind of multiplication, it plays well with multiplication and the opposite, which is division. It doesn't really handle addition and subtraction well. Another simplification strategy. It's just kind of determined in math that if we have a fraction with a square root in it, we would prefer that square root to be in the top, to be in the numerator, rather than in the denominator, rather than in the bottom. So if we see a square root in the denominator, we multiply top and bottom. So here's an example. 10 over the square root of 2. We feel like, if they're going to have a square root, I'd rather it be on the top than the bottom. We multiply by root 2 over root 2. Just whatever radical we don't want, multiply top and bottom. In the top, we have 10 times the square root of 2. In the bottom, square root of 2 times square root of 2 is just 2. Right? This is a rule that always works. Square root of a number times the square root of a number is that number. And then this reduces. Right? If it's not obvious to you, you can think, oh, this is like 10 over 2 times root 2 over 1. So the simplest version would be 5 times the square root of 2. Over here, I don't like that square root of 3. The 2 is fine. I don't mind that 2 in the denominator. So I can multiply top and bottom by the square root of 3. In the top, I get 6 times the square root of 3. In the bottom, I get 2 times, well, square root of 3 times square root of 3 is 3. So I have 6 times the square root of 3 over 6. That just simplifies to square root of 3. You'll be practicing these. And then the last bit in this preliminary handout is reminding ourselves about the Cartesian coordinate system. That's where we use the x-axis and the y-axis. And in the Cartesian coordinate system, any point in the plane basically corresponds to 2 numbers, an x-coordinate and a y-coordinate. So something you should be able to do, just about roughly by hand, is to draw an x-axis and a y-axis, count out a few units, and then plot these points. So if you're doing this for the first time, pause and try your best, then resume when you're ready to see my answer. I will assume people have paused. The x-axis we draw horizontally. The y-axis we draw vertically. And let's just count out 1, 2, 3, 4 in this direction, 1, 2, 3, 4 in this direction, 1, 2, 3, 4 in this direction, 1, 2, 3, 4 in this direction. Graph paper makes it prettier, but you should be able to draw something decent without it. So the point 4, 0 means the x is 4 and the y is 0. From this point right here, we will go 4 units in the positive x direction. That's to the right. And we will go 0 units in the vertical y direction. So here, I'll color code them. There is the point 4, 0. Let's still see that tick mark. So there's 1 point. Negative 1, 2. Oops. Negative 1, 2 means in the x direction we go negative 1. We go backwards, we go to the left. In the y direction we go 2 up. So 1 to the left and 2 up gets us there. Here, I'll do one in green. 0, negative 1 means x, we don't move. Y, we go down 1, so it's negative. And let's do this last one in blue. 2, negative 3 means the x-coordinate is 2 forward. The y-coordinate is 3 down. So 2 forward and 3 down would land us here. And this point right in the middle, where the x and y axes cross, right, that is the point where the x-coordinate is 0 and the y-coordinate is 0. And our name for that is the origin. I will use the word origin much more frequently than I would say the point 0, 0. So it's important that you know this. Otherwise, you'll get confused. All right, there is a lot here. In class, we will have a lot of time to practice these things, but that is the end of this video.